Okay, so again, we're going to do some runs just to show you how to compile and how to run on through our queuing system. And then I'm going to talk about some more advanced things, what's parallel computing, things like that. I'll start out by introducing myself again. I'm Dave Turner. I'm the application scientist here. Kyle Hudson and Adam Tigert are our system administrators. Dan Andreessen is not here. He's the director of the Beocat group. So I'm going to back up here and start by showing you an overview of what Beocat is. I know that Kyle talked about some of this on Monday, but I want to reiterate this because this gives you a big picture of what Beocat is and what its capabilities are. We're running Gen 2 Linux. That's just the flavor of Linux that we run, and a Sun Grid Engine queuing system. So I'll refer to this as SGE, or the queuing system. When you get on the nodes, you log into one of the head nodes, Selene or EOS. Then you use the SGE queuing system to actually run your jobs on the compute nodes. So SGE is your link to doing the actual computations. We currently have 3,252 Intel Xeon compute cores in 145 nodes. 54 of them are the newest Hero nodes. These have the Haswell processor. Each of these has 24 cores and somewhere between 128 and 512 gigabytes. It has 40 gigabit per second Ethernet on, but we're running what's called a low latency RoCE, or RDMA over converged Ethernet over that. So you get 40 gigabits per second with a latency of about 1.5 microseconds. A latency means that even if you send a very small packet, it takes a certain minimum amount of time to send that information. So for small packets, small messages, your communication time is dependent entirely on the latency or the overhead to handshake. For large messages, your transmission time is totally dependent on the bandwidth you have, or how much data that you can push over that communication link. We have 85 ELVs. These are a few years old, but still very, very good machines. These have either 16 or 20 cores in them, and a lot of them have 64 gigabytes of memory. We have a few that get as large as 384 gigabytes, though. The networking in this is called QDR InfiniBand. InfiniBand is a custom network made for cluster computing. And again, that's very fast, about 30 gigabits per second, and again, the same low latency of about 1.5 microseconds. We have 6 mages that are older, but still very useful for especially large runs. 80 cores per mage and 1,000 gigabytes. That's 1 terabyte of memory. So if you need to run really large jobs, the mages are ideal. They're quite a bit slower, but you have all the memory there that you need. If you need speed and large memory, then the Heroes are a good place to run, but there are fewer of those that have 512 gigabytes. We are also resurrecting the old Paladins. We're going to be putting some NVIDIA GPU cards in. I'm not going to really cover programming with GPU cards at all, but just to let you know that they are there. We're also going to have Intel PHY cards in some of the Heroes. Intel PHY cards are coprocessor cards that plug into the PCI bus. This again is more difficult to program, so I won't say a lot about these Intel PHY cards at all. All these machines are connected up to our file server, which has about 2 petabytes. They're connected via either 10 gigabit per second or 40 gigabit per second Ethernet, so fast interconnect. So that's just giving you an overview of Beocat. So hopefully you've all logged in. If any of you have trouble getting in, raise your hand and Adam and Kyle can help you with that. Again, make sure you copy all the slides from the Beocat workshop directory on my home directory to the tilde. The tilde will copy it to your home directory, is what that means. And then if you do a CD into that directory, that'll get you to where we're going to do all our work. I've also put a copy of these slides in the subdirectory called slides. I think I called them Beocat slides, and I put them in a couple forms. I'm sure I put at least PDF slides. So if I go too fast here today and you're still trying to do some of the demonstrations while I'm continuing to talk, you can pop up that PDF and see the directions. We'll be submitting other jobs, so let's skip past this. Okay, so Kyle covered using KStat, and I just wanted to reiterate some of this because it's the best place to get a good picture, a good quick picture of what's going on the nodes. SGE tools have QStat and QAccount to see what's currently running and what has finished. KStat kind of puts that all in one place. It presents it to you in a little bit better form. It colorizes things to tell you if you if there's warnings, it'll start by warning you in yellow and then slowly progress to red, background red, flashing red. If you see something on your job that's flashing red, that's something that needs your attention. If you don't understand what's wrong, then you need to communicate with us. Every day I'll look at this and I'll email people if I see anything wrong. But please feel free to play around with this. You can start by doing KStat minus help, and that'll give you a lot more information than what I wrote here. This bottommost one is also very important. This is probably the one that you'll use most often. KStat minus Z gives you just a synopsis of what your jobs are doing. So it'll kind of get rid of all the other jobs on the nodes you're running on. And even in the queuing system, it'll just show your job in the queue. Now, it won't show you where you're at in the queue. If you want to know that, you have to look at the full queue with a KStat minus Q, for example. Other things that people I don't think use much are KStat minus C is a good way of seeing what everyone is doing. So if you do a KStat minus C, it gives you a summary of who's using the cluster. Again, the color coding in this case is just if you're over 10% of the cluster, you get yellow. If you're over 20%, you get red. It doesn't mean anything's wrong. It just means this person, KH Lee, is using 27% of the machine. What is he doing? It just means he's relentless, right, about getting nodes. So yeah, this is just a kind of a good way of getting an overview of, you can see how many nodes you're running on and how many you have queued compared to other people. But I'll let you guys go ahead and play with KStat. You can do that while I'm giving the talk. And if you see anything that you want to ask a question about, if you see any node that's looking odd, ask me now or ask me after the talk, and I'd be happy to tell you what's going on there. I will tell you that the core count is inaccurate at this point. We made a little bit of a change to the setup of the queuing system, and so you'll see some negative core counts in there. But the load level and everything else should be accurate. Ganglia is another thing that Kyle mentioned. Again, I don't use this as much as I did when I first started here because I use KStat. But if you want to see what has happened over a span of time, Ganglia is a good place to go. You can get charts that'll tell you what happened over the last day on a given machine. So if you're curious about how your job ran, how many threads it's running on, if it's running on all the cores it should, if it's doing disk I/O, Ganglia is a good place to look. Another thing you can do is look at a job with monitor node. To use monitor node, you have to actually have a job running. So if you want to play around with that, one thing you can do is start a job up. If you look in the qs.workshop file that I wrote up, there's a few simple files. One is called hello, for example. You can set it up to run that and then do a sleep afterwards. The sleep will just tell the core to wait a certain number of seconds. So if you do a sleep of 600, that'll wait for 600 seconds or 10 minutes. And then you can try out the monitor node. But what you do with monitor node is you give it the host number or host name that you want to run on, that your job is on. So if you use kstat-z and see that your job's running on Hero 35, for example, then you can do a monitor node of Hero 35, and you can get in and you can poke around a little bit, just as if you SSH'd in. What's typically useful is to run htop. I'll give you an example here by just SSHing in. So let's pick out an interesting node here. And let's just look at ELF8. So I'm going to SSH into ELF8 because I don't have a job there, but I'm the only one. Well, three of us can SSH into nodes. You can't. So you can only look at nodes where you have a job running, and you can get in with the monitor node. But once you're in, this is basically the same thing that you would see is you're just logged in. You can do it in LS. You can do it in htop. And htop will just show you the processes that are running. Now, this is kind of messy, so the most common thing I do is I hit the U key, and then I go down to a certain user, and we'll pick on Quohao today. And we'll see what his job is doing here. And if you go down and look, these are just some of the setup scripts. Here's the bash script. Here it's running a Perl script, and you can actually see the function that it's running is a Perl script called aarex.pl with 12 CPUs. And if you count these up, there will be 12 of those subprocesses that are being used. So if you ever are wondering whether your job is actually running, this is a good way of doing it, is to use monitor node and get in and look at what actually is, what processes are running, and also look at the CPU bars here. If your CPU bars are not 100%, that can be one thing that's a problem. If you ever see a status that's a D, that means that it's in a disk wait. You're doing lots of I/O, and we see some cases where if you're doing I/O to the file server, because our file server currently has some issues. You can see it getting into a disk wait state, and that's an indication that you'd be better off to copy your files to a local disk and run from there, and that's something I'll cover later. But actually getting into the nodes and looking and seeing what the CPU bars are looking like and what processes are running on your nodes are actually very useful, and I don't think that a lot of our users are doing this right now, but that can give you a lot of information. Usually when someone sends me an email saying, I'm not sure my job is running, this is one of the first things that I do, is I SSH in. Okay, so I want to start now talking about parallel computing and go kind of an overview. I'll go kind of historically about computers, and at each stage I'm going to start out with scalar computers, and then at each stage I'm going to add one level of complexity and describe what happened historically. And by that way, I don't want to dive clear into what our current parallel computers look like. By building it up one layer at a time, I think it's a little easier to understand what each layer is about. So in order to do that, I need to go back to the good old days when we dealt with scalar computers. Scalar computer or a serial computer is simply a computer that has one processor or one processor core, and then memory with program data sitting in that memory. So conceptually, it's very easy to understand, and even from a programming point of view, it's pretty easy to understand what's going on. I'm going to take an example of a vector addition here, where you have a vector x plus a vector y equals a vector z. And I've drawn that out here, where again you have these arrays. And with a scalar or serial computer, you just think of this as doing one thing at a time. In order to do this vector addition, you start by simply loading x0, then you load y0, pull them both up into the processor, then you do the add, and then you do a store into the location for z0. Then you repeat for each element. You take x1, y1, add them, store them back down into z1. So this is pretty simple and easy to program, and it's actually how most people think about computers today, even though the way computers operate today is very different. The computers, the way they operate today, do many things at the same time, and they can do many things in many different ways at the same time. But still, most people that program think of codes in a scalar sense. And so part of what I want to get across to you today is that, yes, you can think of it to start with this way, but you also need to start thinking about things in a parallel nature if you're going to use high-performance computers and be able to understand at least a little bit about how to optimize and use them effectively. I don't expect you to understand everything about programming these systems, because most of you probably won't need to actually do the programming, but just if you're using them, even it helps to be exposed to a lot of these concepts. So I'm going to start by showing you a scalar program to do the vector addition. This is in the C programming language. And again, if you don't know C, that's all right. Again, I don't expect you to understand all this. I'll just point out some of what the program does conceptually. because we're going to, as we look at different types of parallel computers, I'm going to talk about the same vector add and show you basically how this changes in the different environments. So we're going to choose a vector length of 1,000,000. The first thing we're going to do in the main program here is to do a print statement saying, I'm starting my vector add. This is just allocating space 1,000,000 times the size of an element, which is a double precision number, for each of the arrays x, y, and z. So we're giving them space. We're initializing each of the vectors. X of I is just going to be I. Y of I is going to be I squared. This is the entire place where we do the work, where we're doing the vector addition. So for those of you who haven't done programming, this is just a general loop. In the C language, this is your initialization, I equals 0 at the beginning of the loop. This is your test. We're going to go until I, or as long as I is less than n, where n is the million. And at each step through the loop, we're going to increment the index I by 1. That's what the plus plus is. So we start with I equals 0. We take x0 plus y0, put it in z0, hit the end bracket, we go around here, we increment by 1, we test, is 1 less than 1,000,000? Yes. So we do x1 plus y1, z1, and we do this until this test is not true. So we do it for 1,000,000 iterations. We're going to do this. At the very end, I have another loop. This one goes from I equals 0 to 100, but the increment is by 10, so it's going to do I equals 0, then 10, 20, etc. This is just printing out the final result, what z is, just so that we have some output. So the first thing I want you to do is actually to compile this. So if you're in the Beocat _workshop subdirectory, I'm going to start you out with the Intel compiler. This is the Intel C compiler. ICC, and then you give it the name of the code, vec_add.c. The .c means it's a code in the C library, or in the C language. The -O, and then this is the name of your executable. You can actually name that anything you want. That's going to be the name when you run the binary or the executable. So the compiler is taking the source code and converting it into the binary code that the machine uses to do the actual running. On Beocat, we have both the Intel compilers and the GNU compilers, which would, in this case, be GCC. In general, I would recommend the Intel compilers just because we're running on Intel processors. But both do a good job. So for now, do the compilation. And then in order to run it, you do a / and then the executable name. The / just means to look in your current working directory. Dot always means the current working directory. So if you do a / vec add ICC, that should run that program.
Could you please repeat what / means?
Yeah, / will choose your directories or subdirectory. So if you look at the screen, I'm currently in my home directory. If I want to do an ls for the Beocat workshop directory, I would do a Beocat workshop and then a /. Well, sorry, that doesn't work, I guess. So inside the Beocat workshop directory, there's a subdirectory called slides. So this command will look in the Beocat workshop subdirectory and then the slides subdirectory inside it. So the / allows you to move between folders.
Yes, but my question was that in a folder, in a current folder, we have a compiled file, but then to run it, we still need
So let me step through it here.
It's because your path doesn't include the current directory you're in. You can change your path variable to include that, but the path variable is basically the list of folders to search for binaries to run.
So I don't actually need to do the // in my case because I've put dot in my path. So it does. The answer does depend on how you set up your environment. And I've got a lot of stuff there. I don't see offhand where oh, there it is. Yeah. So I've actually set up my path environment so I have dot in my path. So I don't actually need to put the //
But you probably do.
but most people will.
Dot is the current working directory. So you're saying
Yeah.
dot this directory /. So that's the directory I'm selecting, then the file.
Right.
How to add current working directory to dot?
So if I look,
I mean, smart variable.
so I have a file called bashrc.mine that gets sourced from your bashrc file. But you could put this in.
You've got path modification on the wiki.
Yeah.
So actually this line here will add dot to your path as well as bin. So export capital path equals dot colon, and then I also add tilde/bin colon and to your path. So you'd want to put that in your .bashrc file. It can go in a bash profile also. Okay, so I went ahead and compiled vec add ICC. So now if I run it, it does the vector addition, and well, it starts by printing that out. It does the vector addition, then it prints out every 10 increments up to 100. Even though we're doing 1,000,000, I only wanted to print out 10. Okay, so that's compiling with the GCC compiler, or the ICC compiler. The GCC compiler is the same. Again, this is the GNU C compiler. You do the same source code. I'm going to name it something different. Again, you don't have to name it this, but I'm just putting the underscore GCC on the end. This case, I'm putting a time in front of it just so that I can do a time and see how long it takes.
I just emailed you with the wiki link.
Now, the time function you can put in front of any executable or any command, and it'll give you the real user and system time. In general, just look at the real time. And this took about 42 milliseconds to run. So I just wanted to introduce you to that. It's useful to use that in your Q subscript at times so that you know where the time is being spent. Other people put a date command in front and behind. So the date command just tells you the date, and then you can subtract between those. But just putting a time in front of your executable is an easy way of understanding how much time is spent in that. And if you're copying files in or out, you can put a time in front of that as well. Okay, so the other thing you can do is edit the QS workshop script. This is a QSub script to run on one core, and then to do this executable, and then you can run it on one of the nodes. So let's look at that real fast. So again, this is mostly stuff, looks like all the stuff that Kyle went over on Monday. Here we're choosing an environment that's a single node, one core on that node. And all I have here is to do the host name and echo hello world. We actually want to run these two things. So I'm going to take these two. So I'm editing this in VI. You can use whatever editor you want. Kyle showed you a little bit about Nano. I've just taken this, everything above the exit line will get run. So it's going to print out the host name, and then it's going to time the vec add ICC, and then time the vec add GCC. And I'll echo out some comments beforehand. Now I'm going to QSub it, and again, I don't have to put any arguments in there because I've put them all in the qs.workshop file. Now we'll wait. So now you see it's running on ELF81, looks like.
Where does it say the core name?
Where does it say what?
The core name?
Say that again.
Where does it say the core name?
The host name?
Oh, I see.
So there it's complete. Now we look at the directory I'm on. There's two new files, workshop.o, and then the user or the job number, and then workshop.po. The PO is always empty. So this is our output. It's dumping out the host name, ELF81. Then it's saying running ICC version. This is actually printed out by the script itself from that echo command I put in there. Then this is printed out from vec add ICC. And this is the time it took, 16 milliseconds. Then again, this is from the echo command I put in the qsub script. This is from the executable itself. And then this is the time, 15 milliseconds in that case. So this is the output from the run.
So in this case, ICC is slow.
No, they're the same speed. This is not an accurate enough time to judge. it's doing a million things, but it's doing a million things that are not much. So in order to get a more accurate time, we would have to give it more work. And on simple tasks like this, both compilers should give you pretty optimal code. The Intel compiler, again, I encourage you to use that more often just because it also has better optimized libraries. The Intel math kernel library has its own optimized versions of the BLOS library, LAWPACK, SCALAPACK, FFT, all those libraries all wrapped in one. So it can be easier to use from that point of view too.
So what version of Intel compiler?
We're currently on version 15, and 16 is the state of the art, and we're working on getting it upgraded. Okay, so this is just showing you what a scalar computer is like, and I wanted to get you some hands-on on how to do some basic compiling and submitting a few scripts. Later on, I'll show you how to do some installations of real software. It's important that you understand how to compile even a single piece of code before you work with makefiles that compile large numbers of smaller C files or source files. Okay, so after scalar computers, Seymour Cray came out with a new technology called vector computing. Vector computers, instead of using silicon chips, used gallium arsenide chips. So a whole new set of technology. And the biggest thing conceptually is a vector computer, instead of working on one thing at a time, in this case worked on 64 elements at the same time. So again, with the vector add, we're going to go over the same vector add, but in this case, instead of doing things one at a time, 64 at a time. So this is a picture of it, larger amount of memory. I drew the memory bus up to the processor as being much wider, because instead of pulling one array element at a time up, you're pulling things up 64 at a time. So you pull 64 elements of X up, you pull 64 elements of Y up, then you add 64 things at the same time, and then you put 64 elements of Z back down into memory. So that's the general concept behind vector computing. Then in the second step, you go to the next 64, and then the next 64. So it's not a big jump conceptually from a scalar computer. It's still fairly easy to understand. What the compilers do is, when they vectorize, is they look at the innermost loop of your code. Now, in our vector add, we only have one loop, so it's just looking at that one loop. But if you have like a double or triple loop, it just analyzes the innermost part of the loops and tries to vectorize that to see if it can do the same thing 64 at a time. There's cases where it can't. There's cases where some elements depend on a calculation from the previous part of the loop, and it just can't vectorize. But potentially, you get a 64 times speed up with these machines. These are some pictures of the Cray vector machines. These were sometimes referred to as love seats because some of the computer is up here and some of it is down here, but these are actually padded seats that you could sit on, kind of like a love seat, I guess, type of one. So real expensive, tens of millions of dollars, but these were the state of the art now. Your phone is faster than these. Your phone now will do a lot more computations than what tens of millions of dollars worth of hardware could do before. Now, when you're doing things 64 at a time, it's important that every loop is vectorized. This is true with parallel computing in general. So I'm just going to take an example application. So let's suppose the application has 3 loops, the first one taking 30 seconds on a scalar machine, the second taking 20 seconds, the third taking 50 seconds. Well, let's say that the first and second loops vectorize, but the third loop doesn't. That means the time taken for the first loop is going to be 30 seconds divided by 64. So we get a 64 times speed up. Second loop is going to be 20 divided by 64, but the third loop is still going to have that 50 seconds in it. So the total time goes from 100 seconds down to 50 seconds. Well, that's doubling the performance of your code. Okay, but we would like to see closer to a 64 times increase. So what I'm trying to get across here is, in order to get your code to vectorize or parallelize and get a good speed up, every part of your code needs to be vectorized. It's that last little bit that has the trouble that will cost you in the long run. And that's one of the things that makes vectorization or parallelization difficult. So again, if all of them are vectorized, then you get 64 times speed up. This may not, and there's other reasons why it may not be 64. Maybe you get a 60 times speed up. That would be pretty good in most cases. But at least you're getting the majority of your potential speed up. Okay, so
what are the main reasons that you cannot vectorize the loop?
The main reasons, if you have a print statement in there, it won't vectorize. Conditional statements make it hard to vectorize because you're doing 64 of the same thing each time. So if you have a conditional in your loop, you're really saying, if this happens, go through this instruction set, otherwise go through this instruction set. Well, you really need to be doing the same thing at each step. So the only conditionals that can handle are the simplest ones. If you have conditional branches, those are tough. Some cases, each time you go through a loop, you're building on what happened in the previous part of the loop, the previous iteration. And that won't vectorize at all because each iteration is dependent on the previous one. So you can't do them all at the same time. You have to do them sequentially. Okay, so gallium arsenide technology was developed entirely for vector computers, very expensive, and eventually people figured out, well, there's a better way. We're building all these small computers. We have the economy of scale. We know everything about silicon. Let's just keep pushing that technology forward. But what can we do to work on these big problems? And in the late 80s and early 90s, what we started doing is building what's called cluster computers. And this is where we start getting into something similar to what Beocat is. Cluster computer is many computers networked together. So if we wanted to, we could take all your laptops, network them together. Well, we have wireless in here. We have Wi-Fi ports. We could do this. Adam, 10 minutes? You want to wire these all up? We needed things like a common file system. A little difficult since he doesn't know your passwords, but you can crack all their passwords in a few minutes, can't you? I have overconfidence in your abilities. So, yeah. So a common file system, and then you need software that would allow you to communicate, and that's commonly what's called the message passing initiative, or MPI software. But we could actually make a cluster computer out of your laptops here. I've taught a couple workshops, one down in Mexico City, where we actually did that. It was a 2-week-long workshop. We had 40 people, not with laptops, but with wired-in desktop machines sitting there. So we just set up everything on the spot to be a large cluster for them. So lots of desktop workstations, anything like that you can make into a cluster computer. These days, it's easier to just go out and buy a cluster computer, rack-mounted everything. So again, many computers network together. The computers are cheaper because you're using the same, we're basically using the same processors in our Beocat nodes as you can get in your laptops. Just a little higher end, a little bigger memory, more cores, stuff like that. So this is a very cost-effective way of getting more computing power, at least. Now, there are catches. The programmer must distribute the data across the compute nodes. So whoever the programmer is has to sit down with their application and decide, well, how is this going to go on all these computers? With parallel computing, you're actually running typically the same program on each computer. So I've just diagrammed here a two-node or two-compute node cluster. If you run a parallel program on this, you'll run one program here, you'll run a second one here. It's almost always a copy of the first one. So you're doing the same program. Each side will just operate on a different part of the data. The computers must usually exchange data in order to perform most calculations, and that's why you want a fast network in between. So again, let's take the simple case of our vector add. Now, I've been doing this for a long time, so I've decided to put all the red array elements on one compute node, computer 0, all the green odd ones on computer 1. By doing that, x0, y0, and z0 are all in the same place. So that computation can be handled by computer 0 without any need for any communications at all. So basically, computer 0 is doing half the computations. Computer 1 is doing the other half. You don't have to communicate. Well, that's a good thing. If I wanted to, I could have given the first half, everything above this, to one computer and everything below this to the other. Same difference. There's no need to do communications for this simple of an algorithm because I divided the memory up between the computers correctly. Now, if I put X on this computer and Y on this computer and wanted to do all the Z calculations here, I would have to do some communications. That wouldn't be the better way to do it because communications costs you time, and then you wouldn't get a 2x speed up. You'd get something less than a doubling of your performance by using two compute nodes. This is too simple of an example, but I want to show you that distributing memory across the computers is the first part of determining what your algorithm does. Another simple algorithm to do on a single processor is to do a matrix multiplication. That's all it is right here. To do a matrix multiply, again, written out as this. To calculate Z0, so I and J are both 0, I need 4 multiplications summed together. So to get Z0, or Z00, this element, I need X00 times Y00 times Y00, then X01 times Y10, so that times that, and X02 times Y20, so that times, sorry, I'm going down this way, going across this way and down this way. And then X03 times Y30, so that times that. So I've gone and divided this up amongst 4 processors right now for computers. And everything in red, I've started out on computer 0, green, blue, and lavender, I guess I'll call that. This is very simple if you're doing it on one computer where all the data is in one node. You can write this up in basically a double loop, or one loop, sorry, a loop over I and J, and then an inner loop over K. So it's a triple loop, but it's this much coding on a scalar computer. When you try to parallelize this, it gets very difficult fast. And this is where there's been a lot of experimentation done with many different algorithms to minimize the amount of communications. One thing you might try or think about doing initially is saying, well, I'm going to do all the Z calculations on my home node, but I'll just start by having all the X elements set to every other node. So every other node has a copy of the entire X array, and do the same for Y. It has a copy of all the Y elements. Then I'm done with my communications up front, and I can do all the computations, and at least they're divided up. Well, you're doing a lot of communications up front. If you go on more than 4 nodes, if you start scaling up to thousands of nodes, then you're yelling at all the other nodes up front, and you get a lot of contention for communication channels. The other thing you run into is these are 4x4 matrices. What happens when they're 10,000 by 10,000 size? You don't want to redundantly store those matrices on each node. You want to divide those matrices amongst all the nodes and then just pass them around a little bit so you don't have to redundantly store all the matrices on each node, and you eventually exceed memory in most cases. So this is an algorithm that doesn't redundantly store the matrix subblocks, and it does the communications while computations are being done. Now, that's also important. If you're doing communications at the same time as computations, you can hide that communication time behind the computations. So while each computer is doing the computations, the network can be doing the communications to get ready for the next set of computations. And if you do that and do it well, then you may not see any effect from the communications at all. And we might see a 4x speed up in this case, and you might be able to scale up to thousands of nodes without seeing any degradation to the communications. I'll just go over very briefly what the algorithm actually is, just to show you that it can get complex. In order to really understand this, you'd have to get a pencil and paper out and diagram it out and work your way through it. So I don't expect you to understand all this. I just want you to understand a little bit about the complexity of what some of these algorithms do. So the first step in doing these communications, so we start with the data as it is shown here. The first step in this algorithm is to broadcast the diagonal blocks of X down each row. So what are the diagonal blocks? This subblock in red is on a diagonal. This is on a diagonal. These are off-diagonal subblocks. So this subblock gets sent down to all the nodes in its row. Well, that's 1. So we're sending this data to computer 1. This data gets sent to all the nodes in its row. Well, that's there. That means it's just sending it over to here. So now we're replicating one subblock only, not the entire X matrix. The next step is to multiply X blocks with each node's Y blocks that you have available. So currently on this node, we have our own X subblock, and the X subblock that came in. And if you go through, what we want to do is for each of our Z values, see which ones we have data in the same place for now. So again, for Z0, we can do x0 times y0. We could do that before. We can do x01 times y10. We can do that before. We also need to be able to do x02 times y02. Well, we can't do that one yet still. But there are going to be some other ones on this node that we can do. So let's go to the next step. Now we're going to shift the y block to the above node. So this y block is going to be shifted above it. Well, that means it gets wrapped down. Since there's no above, we're going to cycle it and go down. This y block gets shifted up here. And then we're going to see if, and the same over here, and then we're going to see if there's more contributions to our z elements that we can do. And by this time, the y20 and y30 are up here that we need to go with our let's see, sorry, x20 is, our x20 and 02 were already shifted over here, and our y20 and y30 were shifted up here. So now we can do the last two elements of z00. Everyone got that straight? No one confused? My whole point in doing this is to show you it gets complicated very quickly. This is the very efficient way of doing a matrix multiply that's very simple to do on one compute node, but very difficult to do when you start doing message passing. You have to be thinking in parallel. You have to be thinking, where is my data at? You have to be thinking, how do I get it to the node? How do I get all the data to the node where I need to in order to do the calculations at the right time? So actually doing the programming takes a lot of practice. So again, I'm not trying to teach you how to program. I just want you to understand a little bit about the complexity. So I also want to show you some of the actual commands that do the message passing. Again, doing the message passing, it's a library called MPI, or Message Passing Initiative. All these that are highlighted in yellow are MPI commands. And this is how you manually communicate from one program on one node to a program on the other node. So when you start up a job that's a message passing job, you start it with a script called MPI run. MPI run is just a script that launches all the jobs on all the computers that you tell it to. But then you have programs running out on the various computers. The very first thing they need to do is they need to know about each other. So the MPI init is the way that they handshake and say, hi, I'm over here on node, such and such. The next two commands are the way for each of the programs to get the number of processors and put it in that variable and which processor number they are. So if you're running on 16 machines, nprocs will be 16. myproc will be a number from 0 to 15. So each of the different programs that are running the same job will have a different processor number. I use the variable myproc. A lot of MPI will use the word rank as which rank are you. These three functions are at the beginning of every MPI program. So if you look at code and see anything with the MPI underscore, it means that code is doing message passing. And when you compile it, you're going to have to compile with MPI CC or MPI Fort for a C or Fortran compiler. And you're going to have to run with MPI run. There's also an MPI exec command that does the same thing. But other than that, this is a C program. It does a lot of the same things. In this case, what this program is designed to do, it's called a ping pong. So we're going to run this on two nodes, two computers, And we're going to send a message from computer 0 to computer 1, and then from computer 1 back to computer 0, and that's it. So this is our message. I'm going to send the value in this variable, which we're going to start at 0. Now, again, as the programmer, it's my job to divide up the workload. And the entire workload and data distribution is always divided based on the processor number, because that's the only thing different in the code on the different computers. The code is the same. This one variable is how you differentiate those runs to decide what part of the data is going to be operated on, or what do you do differently. So in this case, if myproc equals 0, I'm going to do these commands. If myproc is 1, the second processor, I'm going to do these commands instead. Otherwise, both jobs run through here and do everything the same up to here and everything the same after there. It's just that one will run through here, the second will go through here. So the first one does a send from, again, this is processor 0 to the destination node, which is 1. It's going to send this variable, 1 integer, to the destination. Then it's going to sit there and going to wait for a response. This is a blocking wait. When you hit a wait, it just waits forever until it gets a message back. So the second computer skips all this and goes here. It's going to start and block on a message coming in from the first node, source 0. It's going to wait for 1 integer from source 0. And so it'll just sit there and wait until the first computer 0, sends a message out. Then it receives it. It's going to increment that variable 1 by 1 and then send it back. Then computer 0 can finish and gets its message, and they both print out what the final value of that variable is. So again, over here is our 2 compute node cluster here. This again shows the order of everything is the numbers. Anything in red is what computer 0 does. Computer 0 starts with the token set, the variable set to 0. It sends it to processor 1. Then it hits the receive, so it has to wait there. It can't do that yet. The third thing that happens is the receive from process 0 of the message. And again, the message is just a variable. Excuse me. And then it increments it by 1. So now the variable is 1, and it sends that back to process 0, compute 0, which is on this computer. And then that finishes up its receive, and then they can both print things out. So the message gets sent this way, and then the second one comes back here, and it's done. Questions? Okay, let's actually compile that and run it then. Again, when you compile an MPI code, instead of going directly with the Intel or GCC compilers, you compile it with the MPI. It's a wrapper around the Intel or GNU compilers. So these still call the Intel or GCC compilers, but they also set up the include files and or include paths and the libraries that you need for any MPI program. So for a C program, you use MPI CC and give it the source code, and then again we're going to name our executable. And you can run this to start out with just on Beocat on the head node. So let's go ahead and do that. So here it's going to compile it. So now we have an executable called token pass. Now we can't just run it. Well, okay, we can, but it's only running on one thread then. So what we can do is then give it 2, tell it to run on 2. So now it's saying before init, after init, hello from 0 of 2, hello from 1 of 2. So those are just some print statements I put in there. And then at the end, it's saying process 0 has token 1, token equal 1, so the variable token is set to 1. Process 1 has the token equal to 1 as well. So in computer 0, we never did increment the token. We did increment it in computer 2. The way that it got set to 1 for computer 0 is that we sent it to computer 2, it incremented it and sent it back. So that's showing that, yes, we did get it back correctly from the second node. So a lot of you, when you get to running actual applications, will need to be able to use MPI run and MPI-CC and things like that. So again, I just want to expose you to these things. You don't have to understand all of the send and receive commands and things like that. I just want to make sure that you know when you see something like that, that, hey, that's doing message passing. Okay, I've showed you 2 and 4 node clusters. It can get a lot more complicated than that. You can get different network topologies. Anytime, a lot of network switches will get you up to around 40 ports. So if you have 40 computers, you can plug them into the same switch and say, fine. You don't have any network topology. All of them can talk to each other at the same time without any contention for communication channels. You can also make more sophisticated networks that are also non-blocking out of smaller ones. Let's skip that for now. The other thing you'll see if you move up to larger supercomputers is actual network topologies like this, where each of these is a computer or a compute node, and this is a 3D grid network. So each node has 6 communication channels in a 3D mesh. So you talk to the nodes above and below, in front and back, and to either side. A lot of these types also have the wraparound feature. So if it's on an edge, it wraps around and talks to the one on the far end. That's called a 3D torus instead of a 3D grid. So this is a picture of Blue Waters. Blue Waters is a computer at NCSA in Urbana-Champaign, a $50 million computer. I think it's got around 100,000 nodes. A lot of what we've talked about is dividing work up among just a few nodes. If you have to do data layout on a very large system like this, you have to be careful that you're not talking from a node way on one end to the way on the other end, because there's just not enough communication pathways to handle all of them shouting at each other. So if you did something like a 3-dimensional FFT where you have to transpose the data, it just would not scale well on this. On a system like this, it only really works well if you localize your communications. So if you're only talking to your neighboring nodes, You can talk to, they can all do a shift simultaneously as long as it's just to your neighboring nodes. A matrix multiply does that. The algorithm that I briefly showed you is doing shifts to the neighboring nodes. It will cycle through them, but each shift in itself is just to the neighboring nodes. So that's an algorithm that would actually map well on these larger systems. Okay, so let's continue on. What I talked to you about is running on multiple nodes. Around 2003, computing changed again, and instead of building clusters of large single processor machines, we started seeing dual processor or dual core machines come out. Around 2005, it was quad core. Well, now we're buying machines with 16 cores for the elves, 24 cores for the Haswells, the heroes. So you get a whole lot of computing cores in each box. So each of these is essentially a computer in itself. In this case, you're sharing memory, though. If you run a multiprocessor job in this environment, you're still usually using the same code for each of these processing cores. It's again just operating on a different part of the data. And again, since you can do shared memory within a multi-core computer, all those processing elements can be attacking the same area of memory at the same time, rather than having to pass messages around. Now, you can still do MPI and do that where each process would have its own area of memory. And in that case, instead of sending messages around over a network, you're just doing memory copies between the memory space for the different processes. So it's fairly efficient. It's convenient in that you can do message passing between nodes and then use that same code when you're working on a multi-core computer, where if you do this shared memory programming, that works only within one multi-core node. It doesn't work when you try to go beyond one. OpenMP is the main way that you program multi-core systems if you're not going to use MPI. This is a lot easier to program since, again, you're not manually passing around messages. It's fairly efficient since, again, all the data is not being moved around. But the limitation is you can only do this within one compute node. With OpenMP, you start one job, but it can be then spread over many threads, with each thread running on one process typically. This is an example where you start a code, then when you hit a loop where there's a lot of computations to be done, it'll spawn off many threads. So if you're running on 16 cores, you'd run typically 16 threads. Then when it's done with that loop, it'll collapse down to the master thread and do the scalar sections. Next time it hits a loop with a lot of work again, it'll expand and put one thread on each of these processing cores. And each one of those will work on a different part of the loop. It'll collapse down. So again, that's kind of what happens in OpenMP. And it's really fairly easy to do this type of programming. This is an example of, again, the vector add code. And again, I'll show you just the things that I changed. One thing I did here is we're setting the number of threads with an OMP for OpenMP set num threads to 4. So we're going to set our default number of threads to 4. We're going to print out how many threads do I have here. When we run this, you're going to see when we get here, even though we set the number of threads to 4, this is going to tell you that there's only one thread running. This is because we are not in a loop yet. We haven't hit that part where we want to spawn off additional threads. This is the same allocation and initialization. Here is the one main difference here. This is where we tell it with a pragma to do OpenMP, parallelize this for loop. The loop is the same. We're just telling the compiler that if you're doing OpenMP, spawn this off onto as many threads as you're given, which in this case is 4. Now I put this in here, so the first time through it's going to print out how many threads are we using within that loop. And then the end is the same. So again, let's go ahead and compile this. When we compile this, use either the ICC or GCC, doesn't matter which, but we have to tie in the appropriate library. If you do ICC, you have to put a minus OpenMP. If you do GCC, minus F OpenMP. So I'm going to use the ICC version. And when I run it, you see that the first thing it says is even though we set the number of threads to 4, it's only using 1 since it's not in one of those loops where we gave it the pragma and told it to spread that amongst 4. But when it does the actual vectorization, or the parallelization in that loop, it actually is using all 4 threads. Okay, the other thing you can do with this is if you comment out, so I manually set it within the code to use 4 threads. If you comment that line out with a double slash, then it won't automatically set any number here. And if you run it, it'll just default to 8 on the head nodes. But you can set it with this environment variable too. So if you comment this line out, recompile it, and run it again, this will use 8 threads. But then you can set this environment variable to 2, and this will use 2 threads. So if you're running multi-threaded stuff, you in general don't want to set the number of threads in your program. When you use your qsub file, that'll automatically set the number of threads to the number of slots or number of compute cores that you ask for. So this is one thing that will come up if you're doing OpenMP jobs that you're running. Okay, I see we've already lost Adam. All right, so we're getting closer to what Beocat actually is. We've gone from scalar, we've talked briefly about vector, then parallel computing between nodes, then multi-core within a node. Well, the next step is to combine the last two and do multi-core and multiple nodes. And again, in order to do this, if you want, you can do MPI between nodes and MPI between cores of a node. So that's maybe the easiest because you only use one level of parallel programming in that case. This is done a lot of times because more for historical reasons. You'll see a lot of codes that have been around for 2 decades that were programmed in MPI because OpenMP wasn't available. Now they run fairly efficiently, even multi-core, so people just don't put the effort in to do OpenMP on top of MPI. And again, this is a better picture of what MPI within a node would be. If you ran on these 8 cores with an MPI job, each core, each job on each core would have its own area of memory, and when you did message passing, you would just copy data between those areas of memory. If you want, though, you can do MPI between compute nodes and OpenMP within a compute node. This is the most efficient. It's called hybrid computing because you're doing 2 levels of parallelism, so more work, but that's probably the optimal for efficiency. One more layer of complexity. I know things are getting more complicated, but we're actually getting close to what Beocat actually is. We're back to vectorization. So all that stuff I said about vectorization before, well, now it's starting to show back up. Our ELF nodes can do a vectorization of vector length of 2 doubles. So they can do 2 double precision numbers, 2 double precision computations at the same time. The Haswells, which are our hero nodes, can do 4 doubles at the same time. So if your code can vectorize, that means either it's automatically vectorizing or you get in there and make it vectorize so it's doing 4 of the same thing at the same time. You can potentially get a factor of 4 speed up. The Intel Phi processors that I mentioned have 512-bit units, 512 bits for a 64-bit double that allows you 8 doubles at the same time. The Intel processors that will be out in about a year are going to have these same 512-bit registers. So within a year, your code needs to vectorize or you're losing a factor of 8. That's enormous. The big problem is that right now, almost no codes are vectorizing well. Of all the scientific codes that we've run on Beocat, if anything was automatically vectorizing, we should see a factor of 2 difference between the runtime on the elves compared to the heroes. And we're just not seeing that. They're getting about the same time. So almost nothing is automatically vectorizing. The next round of processors, the hardware will change so it'll make it easier for things to automatically parallelize or vectorize. I've gone through and tried to manually vectorize a few codes. You basically have to make sure that all your big arrays are aligned to 64 bytes. So in C, there's some help in doing your mallocs to align things to 64 bytes. But then before each loop, you have to tell the compiler that those arrays are properly aligned. You may also have to tell it, give it some help if it has trouble. And I've tried working with this, and right now I've found that the Intel vector compilers are buggy, and I haven't had much luck with it. So I'm hopeful that when we upgrade to the version 16 of the Intel compilers, that they're better. I've also got access to an expert in Intel so that I can report bugs to them, and if they have any advice for us, they can pass it back. If you want to actually try this on a simple code like the vector adds, try doing this with the code being the vector add. This will generate a report. And I included that report somewhere here. This is what you get as far as help from the compiler. when it gives you a vector report. And just quickly, it's actually doing something useful. It's saying that it fused the loops at line numbers 19 and 29. I have a setup loop, then I have the loop that actually does the vector add, and it fused those together automatically. Now, this is an example. I didn't want it to do it. I should just put a print statement in there to keep it from fusing, but that's fine. So it'll give you a lot of remarks telling you whether each array is aligned or unaligned. It does actually say fuse loop was vectorized. Entire loop, okay, let's ignore that. It can give you information about striding. Here's where it actually gives you an estimate of the speed up. Scalar loop cost is 23, whatever 23 units is. The vector loop, it estimates, is 9.5. So it estimates a speed up of 2.4. Not sure how it does that because I didn't really tell it if I'm running it on an ELF or a Haswell. I assume it's just taking the head node information, but the head node is what? It's not a Haswell.
No, it's Westmere.
Yeah, so it should be a factor of 2 max. So I don't know how it's getting that estimate, but this gives you some idea of the information it gives you. Most of you will look at that and say, I don't want to ever see that again. If you want to vectorize your code, the proper answer is to email me. And I may tell you, well, it's not ready yet, but if you want, this is, so the best approach is there's a lot of codes where the developers are putting in effort to vectorize them. I haven't heard of a lot of successes yet. But there's a classical MD code called GrowMax that is one of them that's receiving extra attention from the developers and from Intel, as well as a few others that we use around here. There's a biology code Mazurka or something like that. Anyone know? That's also getting a lot of attention. So there's about 20 codes that are getting a lot of attention, but Intel is a little behind on this, and everyone needs to be vectorizing as of a year from now. Okay. So anyway, again, I just want to expose you to this stuff so that you know what the current status is on some of these issues that you're going to be needing to at least know about when it comes to optimization. I really won't spend much time on this. I put it in there more for information. When it comes to optimization, this is more information that I need to know or I need to deal with. This just shows you that before I was showing you a processor and memory, there's actually many layers of cache that the system automatically manages in between the processor and memory. The closer that you are to the processor, the faster it is, the memory is, but the more expensive it is and the smaller the amount is. So you can see the speed here, only 128 gigs of L1 cache, but it's 700 gigabytes per second to get it up here. Where clear down in main memory, here you can get close to a terabyte of memory on the Haswells, but it's 17 gigabytes per second to get the data up. So a lot of optimization is trying to keep the data that you're using up here and reuse it as heavily as possible before you have to shift it out. Okay, and just briefly again, I'll reiterate the goal of all this parallel computing, whether it's vectorization or parallelization or whatever, is to try to get an n times speed up on n processes. That doesn't happen a lot. Inefficiencies can come in quite often from communications. So even if you're doing multi-core stuff, if you're running on all 16 cores, you're sharing the main memory bus. So even if you're running fairly efficient code, since you do have a shared resource of the shared memory bus that can cut your efficiency. If you're doing multiple node stuff, your communication between nodes is going to be your primary source of inefficiency. If your load is not balanced, that can get in there. But ultimately, this is the goal is ideal scaling. I think we could skip that too. That's just some ultimate performance that I talked about earlier. So one of the common questions that we get is, how many cores should I run on? When you start your job, one of the first things, if it's a new job, a new application that you haven't used before, one of the first things that you should probably do is do a scaling study. Measure the runtime of the application on 1, 2, 4, 8, and 16 cores. Then you can make a graph like this. So again, in each run, you do a time of your executable. And this is just a sample. Let's say on 1 core it took 10 hours, on 2 cores it took 5 hours. Well, that's awesome. That's a 2x speed up on 2 cores. But if you run it on 4 cores and it takes 2.8 hours, that's less than ideal scaling, but it's still pretty close. 3.6 times, we would like to see it at 4, but that's very reasonable. Then you go up to 8 cores, you're down to 1.5 hours. That's a 6.7 times speed up on 8 cores. That's still fine. But if you go up to 16 cores, 1.1 hours, and it's down to 9.1 times speed up, well, now you're getting to only about half efficiency, and I would probably recommend not using quite 16 cores. Your runtime is going to be faster if you use 16 cores. It's going to take you longer to schedule, and it's going to be more wasteful of the resources. And, you know, we have to share the resources amongst others. So we'd like to have you above a 50% efficiency. You know, closer to 70% is good. The other thing you do when you're starting to run a code is you may not know how much memory it takes. About all you can do is run it once and look with KStat. KStat will tell you the actual amount of memory that's being used. And if it's more than what you requested, kill it off, ask for more, and restart. That's really all you can do. When I write a code, I usually write in an estimate for how much memory it uses, but almost no one else does that. So you really have to just do it by trial and error. Another thing, yeah.
If the same job can have a speed up with 2 times running on 2 cores, why cannot get the same speed up running on more cores, the same code?
So that's a very good question. Mostly the reason is I'll go back to the slide that I skipped. These are very small graphs, I realize that. This is a very typical graph for the communication performance between 2 nodes. So down here is, for small messages, you have the latency. So no matter what your message size is down there, it's going to take us 1.5 microseconds. So the size of the message doesn't matter too much. Up here, the size of the message matters totally because it's the bandwidth that's limiting you for the large messages. The latency no longer makes a difference. In between, you get a little effect from both. So when you start running on 1 or 2 nodes, you're running in this area where you're bandwidth bound. So if you go on more nodes, if you go on twice as many nodes, you're cutting the computations down by a factor of 2, but you're also cutting the communication time by a factor of 2 because your messages are half as large. That's going from here to here. As you keep dividing, though, you start falling off this slope and getting that latency hit in there. So now as you double the number of nodes, your computations are getting cut in half, but your communications are no longer getting cut completely in half because of the small message latency is what you're hitting. So that's usually the case for what happens with the parallel efficiency, the parallel inefficiency for going for larger numbers of processors.
That's true for the MPI, but if you use OpenMPI, it's a totally different issue.
Same effect for different reasons. You're still, with OpenMP, you have 16 or 24 threads all accessing the same memory. Now, if it's the same memory page, only one of those threads at a time can access the same 4 kilobyte memory page. So it depends somewhat on how the application is written up. But you're also sharing the memory bus. So if you have more and more cores accessing that same shared memory bus, so again, if you have more cores sharing the memory bus there, that's where your contention is going to come in, and you're going to get less of a fraction of that performance. Another good question, though. Almost 2 hours in, and you guys are still listening. That's a good sign. Only 2 more hours to go. We do have this till.
You may.
I am kidding. I didn't want to see too many worried looks. We have to listen to Dave for 2 more hours? Okay, so this is one thing I do too, is if you come to me and say, why is my code running slow? If it's an important code and I think I can do something to help it out with, I will put in my own profiling. I have my own profiling code that's just one C library. You put an include file in there. Then around the sections that I want to time, I put a time start and the section name and a time stop. And at the end, I print out this report. And the code does all the calculations to accumulate the times being spent in each function that I put that around. So it prints out at the top the most heavily used one. In this case, this is the bioinformatics code called ABYSS. It tells you how many times it was called, it tells you the name of the function, and the amount of time. So this can really help me to determine where time is being spent so that I can concentrate my efforts on increasing the computational time. If it's area of communications, I can track that. So this is one thing that I can put into codes that help me, and it's done in a non-intrusive manner. There are external commands like applications like gprof that'll do this, but quite often it's intrusive. And by that I mean if you run an application and then run it under gprof, it'll automatically do this, but the gprof run might take 7 times as long as the actual run, which was the case with this code. That means that the data is useless if it's adding 7 times the amount of runtime. Okay, talk just briefly about optimizing input and output. So as Kyle went over on Monday, we still do have some issues with our file servers. Some of it is the interactive use. Some of it is also if you're operating on large data files, input and output files, you can at times get the system into where it's hitting that disk weight that I mentioned when I was talking about HTOP. If that happens, then what we can offer is to have you move your large files at the beginning of your run to the local disk on the compute node. And that's fairly easy to do. Again, this is all the stuff that you've seen before in your QSub script. All you have to do is copy your input file or files to $temp. $temp is a directory on the compute node that your job is running on. This will only work for jobs that are on a single compute node. So again, if you copy your input files to $temp, then when you run your application, whatever you do to list your input files, you need to list them as being in $temp / and then the name of the input file. Some will take a directory, etc. You also want to do the same with any large output file. So you copy those to your local disk. At the end, this is very important, at the end of the run, you want to make sure to copy those output files back to dot, which is your current working directory. If you do not copy things off the local disk, when your job ends, that gets deleted. So we immediately purge that space. So again, copy stuff in, run your application, copy stuff out. When the Q subscript returns, that gets deleted automatically. Even with our file server problems, we've really never seen where this is slow or this is slow. And then this will be fast. There's about 600 gigabytes of disk space on most every node, so we've only really had one user where that's been a limitation. We've just set up another thing called Scratch. A lot of systems have this. You do a make directory of /scratch and then your username. That'll be Scratch space that you have access to. You do this once, it'll stay there. Things that you put into Scratch may be purged every 30 days.
Not maybe, will be purged.
May be purged in some manner. To be determined.
We have policies already in place.
Okay. So again, then you can externally now just from the Beocat command line, you can do whatever you want. This is just another directory that you have control over. You can copy your input files there. You can CD over there. You can manipulate your files in place there. So it's much easier to work with. Then when you run your script, you don't have to copy things in and out each time. You can if you want. You just run your application, and then whenever you want to access those files, you just tell it to do it from Scratch, Dave Turner, or your username, and then that file name. So then you're giving it the full path, but it's sitting in Scratch. But this is much more convenient. This does allow you to work from using MPI jobs as well, because all nodes have access to this. Any questions about that? I will give you one warning. If you do copy stuff in there, make sure not to do a copy with a -p. A -p preserves the creation date or the modification date. If you copy in things with a -p for the to preserve the modification date, and if the last time you modified that file was more than 30 days ago, the scripts these guys set up are going to delete that.
That's not true because we're using a separate, we're not using that information to point that out.
Okay, never mind.
That was the way we had intended for it to be. That was the last information you got.
They don't tell me anything.
We found a better way. Somebody already wrote a package that has the policies in there.
Okay.
It uses a database backend.
So that'll make it a lot easier. Okay, the last thing to cover is software installation. In general, so first of all, we do have some scientific applications installed. Kyle told you how to get a list of those. But in general, you're responsible for installing your own application on your home directory. This is for several reasons. We don't have the resources, the people to install every code for everyone and keep it up to date. It's also because you know the science and follow the science involved with that package better than we do. And a lot of these things you have to know the science and know what, in order to know how to compile it. A code called VASP, you can compile it in different ways depending on the science, to run with a gamma point only or the standard, etc. We are always willing to help. So we would like to have you start and try it. If you run into a wall, don't hesitate to send a message to Beocat Help, and we will sit down and either advise you on how to get past your problem, or in many cases I end up actually doing the installs because they do get complicated. I can also provide optimization advice, things like a lot of times the configuration may ask you to choose a compiler and some of the optimized libraries, and I can advise on that. So general instructions for software installation: download the package, decompress it, and here's one that people don't always do: actually read the documentations. Mostly they come with either a file called README or install, all in capital letters. And these will be very useful. Mostly they will have very short descriptions of how to do the install. This is the basic way of doing it in most cases. It's a configure script. Normally you do configure, make install, but this would install if you have root access, which you do not have on Beocat. If you just do configure, make install without setting a prefix, it will try to install in root. It'll do what's called a sudo. An email will be sent to Adam and Kyle, and they will make fun of you, not in front of you, but behind you, and say, what are these guys doing? This is absolutely true. So this is the one thing that you need to do that's probably not in a lot of the directions, is you need to set the prefix where you want it to be installed in your home directory.
Make sure you don't get a lot of times you'll see, what we see more than anything else is people trying to go through and use like apt-get. That doesn't work. You have to get the actual source and compile it yourself.
So many packages are more difficult than this to install, and often things just don't work. Even if these are professionally maintained packages, it can be that our system is different, our libraries are different, we have a slightly older version of a library, we have a slightly newer version of a compiler, or the people that manage the software are just plain bad. That's quite often the case.
More often than I would like to admit.
Yeah. We have some quantum chemists back here that can attest to that, right? So this is an example called Mother. This is a bioinformatics code. And in this case, all we really had to do was download it. And they actually have some precompiled binaries. Now, even if you see there's a whole long list of what you can download, it's not always clear to most people whether those precompiled binaries will work. In this case, there was one called mother.cen_64.zip. Now, when I see that, what I see is this is CentOS 64-bit stuff. That'll probably work on our system. So we didn't actually have to compile this. We just uncompressed it, and the binaries were there already. That's always the easiest way, is if there's precompiled binaries. If not, there's almost always the source code, and this will be in a source code. They'll give the version number and a .tar.gz, which are the .tar is the archiving. Archiving is the way to put many source codes into one file, an archive. And then the GZ is the compression algorithm that's used. So again, with Mother, there was no good documentations, no README or install files. So I had to do a Google search for Mother install and found some. They just have you edit the make file and leave you at that. So you have to know how to edit a make file. What's a make file? Well, I showed you how to compile a single file at a time. A make file will take a larger code that's made up of a lot of smaller source codes and header files, and it'll provide all the rules that's needed to combine all those, compile them into one object that you'll end up running, one executable. So at the end, after you type make, you can leave it go for maybe an hour while it compiles, and then you'll have your executable, which is called mother. Another example is this abyss code. This was much more straightforward. Configure. I gave it this place to do the install, but there are a couple other options that I gave it to make it run more efficiently for memory reasons. And then there's also, it depends on another library called sparse hash that I had to compile first and tell it where it was at. But after that, I did a make install, and that was about it. So I showed you that the base way of doing this is 3 commands. It's almost always harder than that. We do want you to try it, and but don't hesitate to come and ask for advice or help. Our offices are up here on the 2nd floor. Mine is 2219, and they're tucked a little further behind. So feel free to send us email.
That way or anything.
Yeah.
Just so you know.
They want me to intercept everyone before they get back to them. So.
It doesn't work out that way.
I fooled them, though. I'm never here in the mornings, so they don't have that barrier in the mornings. Okay, additional information. First of all, we have a lot of information in the Beocat documentation. In the Beocat workshop directory that I had you copy, I put a Unix introduction PDF in there, so if you're not very familiar with Unix, you can go through that. There's also Oklahoma University puts out supercomputing in plain English. You can look through that. If you're more interested in MPI or OpenMPI, this will give you some overviews. It starts out fairly general and gets very complex, so you can stop where you want. And I will stop. Final questions? Comments? Was this useful? I'm trying to expose you to a lot of areas of high-performance computing so that when you deal with these as a user, you'll at least know a little bit or have a little bit of a framework, a little bit of a background about what some of these things are about. So I certainly don't expect you to be able to program in any of these languages or anything like that. No comments? You only have words that you think will be too hurtful for me? Okay, well, we'll adjourn. Thank you for coming.